Welcome to section 11.3, Inference about two means independent samples. Objective 1. Test hypotheses regarding the difference of two independent means. Okay. So to test hypotheses regarding two population means, mu1 and mu2, with unknown population standard deviations, we use the following steps provided the following requirements. The samples are obtained using simple random sampling or a completely randomized experiment with two levels of treatment. So this means that proper random selection or assignment and that the two groups are independent or different people. Samples are independent. So this is the defining feature. So we'd say like group 1 and group 2 are completely separate individuals. The population from which samples are drawn are normally distributed, or the sample sizes are large, meaning the sample size 1 and 2 are both greater than or equal to 30. So in translation, for small samples, we need normality. For large samples, the central limit theorem saves us, because as long as it's large, meaning greater than 30, we're good to go for normality. For each sample, the sample size is no more than 5% of the population size. So this ensures independence within each sample. The next is our symbols. Okay, this is similar to section 11.1 where we discuss the two different proportions. In this one, we're discussing two means. So we want to think of it just like the proportions, but now we're comparing means instead of proportions. So mu1 is the mean for population 1, n1 size of sample 1, mu2 mean for population 2, n2 size of sample 2. Okay. Next, we have our hypotheses. So for our null hypotheses, we know we're using equality. So we'll set each mu equal to each other. Then for the alternative, we have three different types: does not equal, less than, or greater than, to signify the three different tests: right-tailed, left-tailed, and two-tailed. It can also be written as mu1 minus mu2 equals 0. So remember, that's just moving mu2 to the left-hand side via subtraction. Okay. So the idea here is the same as proportions. So we're asking ourselves, are the two means equal, or is one bigger than the other? Okay. Next, we have critical values. Critical values come from the t-table. You can find that in your formula chart, or you can use your calculator, and degrees of freedom. Okay. So remember, the degrees of freedom is going to be smaller than your sample size by 1. Remember to put the appropriate sign on the critical value, whether it's positive, negative, or positive and negative. Okay. So it's important here that we use the smaller of the two degrees of freedom when we are trying to find our critical values, because we have two different sample sizes. So we need to be conservative or safer. So we use the smallest sample size. Okay. Then to find our inferences about two means, we can run a test in our calculator. And the test that we're going to run is number 4, 2SAMP-T test. And this will give us our test statistic and our p-value. We want to answer null to pooled on the calculator. So when you go to the 2SAMP-T test towards the end, after you enter in all of your data, you will see an option for pooled, and we want to say no to pooled. Okay, so not pooled is when data is combined or averaged together, but instead analyze separately for different groups or conditions. Imagine you have a group of friends and you want to know their average height. If you measure each friend individually and calculate the average, that's not pooled data. So you're looking at each person's height separately. So just think of pool and what it means. And it means we assume both groups have the same variance. So not pooled, which is what we're using, doesn't make that assumption. It's safer and more general. So when you go into your calculator, you'll select stats. If you have the summary statistics, so after you go to sample t-test, you have two options, stats or data. So you'll select stats if you have the summary statistics, or data if you have raw data. Then you'll enter in your mean and standard deviation for both samples, and then you'll choose your alternative hypothesis. So in our first example here, researchers conducted a randomized double-blind study to measure the effects of the drug olanzapine on the patients diagnosed with bipolar disorder. A total of 115 patients with SSMIV diagnosis of bipolar disorder were randomly divided into two groups. Group 1 received 5 to 20 milligrams per day of olanzapine, while Group 2 received a placebo. The effectiveness of the drug was measured during the Young Mania Rating Scale total score, with the net improvement in the score recorded. The results are presented in the table. Does the evidence suggest that the experimental group experienced a larger mean improvement than the control group at the 0.01 level of significance? So we have our table here. We have our experimental group stats and our control group stats. Note that, and let me get my pointer here, 55 is going to be N1, 60 is going to be N2. Our mean improvement, so this is going to be our X1 or X bar for the mean, and this will be X bar 2. And then this is standard deviation, so S1, and then this would be S2. So this data here would be considered stats. Okay. So our claim is that the experimental group has experienced a larger mean improvement than the control group, and we took that directly from the problem. So in other words, we're asking ourselves, did the drug work better than the placebo at improving mania symptoms? So our hypothesis will be mu1 equals mu2. Our alternative will be mu1 is greater than mu2. We know it's a right tail test because we are using a greater than symbol. Okay. We're asking if the experimental group improved more than the control group. So we would be using the greater than symbol, and our level of significance is 0.01. Okay. Next thing, we will find our critical value, and we can utilize the calculator, or we can utilize the T table in our formula chart. Inverse T will be the test that we're running in our calculator. Our alpha is 0.01, and our degrees of freedom will be 54. Now, why is it 54? Well, remember I mentioned that we need to use the smaller of the two sample sizes. So we would use 55 and subtract 1, which gets us 54. Okay. All right. Next, we will find our test statistic and our p-value. So we would go into that sample t-test in our calculator, enter in all of our stats as we see here in our table. Make sure to select no pool after you select your alternative hypothesis. Press calculate, and you should get to your test statistic t and your p-value as shown here on the screen. Okay. So in drawing our picture, we have our t-distribution curve with our rejection region shaded, with our critical value 2.397 as our boundary line. We see here that our test statistic is greater than our critical value, so it lands in the reject region. So our decision is going to be to reject the null. Why? Because the test statistic is in the rejection region and our p-value is less than alpha. So we can conclude that there is sufficient evidence to conclude that the experimental group has experienced a larger mean improvement than the control group. Okay. All right, so let's understand this example a little more. So what did we test? We test, or we're trying to answer the question, does olanzapine improve bipolar mania symptoms better than the placebo? That is what we were trying to test. And we found that the olanzapine group improved by 14.8 points on average, and the placebo group improved 8.1 points on average. So if we subtract that, that's approximately a difference of 6.7 points better with the drug. So what was our verdict? Through our analysis, we would say that this is a highly statistical significance because our p-value is 0.0026. So there's strong evidence that olanzapine works better than the placebo. But the practical significance, one would say that a 6.7 point improvement on the Young Mania Scale is clinically meaningful. So this would suggest that olanzapine is an effective treatment for bipolar disorder. Okay. But why do studies like this actually matter? Like, why do we do all of this, and why do we analyze the data for certain drug medications? Well, in the problem, it mentioned that this is a double-blind randomized controlled trial, and that is the gold standard for medications such as olanzapine, because neither patients nor doctors knew who got the drug versus the placebo, which eliminates bias. And if we can eliminate bias, then we can trust the results of the data when testing. Our next example, a music industry producer wondered whether there is a difference in lengths and seconds of rhythm and blues songs versus alternative songs. He obtained a random sample of 30 songs in each music category and documented song lengths. The results are listed below. Test whether the length of rhythm or blues songs is different from the length of alternative songs at the 0.1 level of significance. So we have our data here. Okay, we have X1, which is our rhythm and blues, RB, and then we have our data for the alternative songs, which is ALT. Okay, that's the sample mean and standard deviation. So when we run our tests, we would be using stats to find our test statistic and p-value. So our claim is that the length of rhythm in blue songs is different from the length of alternative songs. That was taken directly from the problem. So we're asking ourselves, do these two music genres have different average song lengths? Okay. Our hypothesis is going to be mu1 equals mu2 for the null, and the alternative mu1 does not equal mu2. This makes it a two-tailed test because we're asking if they're different. We don't know which genre might be longer. And our level of significance is 0.1. So next we need to find our critical value. So we can use inverse T or we can use the formula chart. So since we are a two-tailed test, we then need to take our alpha 0.1, which is the total area, and divide it by 2. So now each tail's area is 0.05. So that's the area that we would enter into inverse T. Our degrees of freedom is 29, okay, because we would take the sample size. He took a random sample of 30 songs for each category. So 30 minus 1 is 29, When we enter that into our calculator, we then get our critical value to be 1.699. Since we are two-tailed, we also have negative 1.699. So when we draw our t-distribution curve with our rejection region shaded on both tails, we have our critical values, positive and negative, of 1.699 as our boundaries. So next we will then go into our calculator and run our sample test. So the two-sample t-test. When we do that, we'll get our test statistic and we'll get our p-value. And from this, we will then be able to make a decision. And our decision is going to be to do not reject the null. Why? Well, because our test statistic, 0.610, is not in the rejection region. And our p-value, 0.544, is greater than alpha. So we can conclude that there is not sufficient evidence to conclude that the length of rhythm in blues songs is different from the length of alternative songs. Okay, so let's understand this example a little more as well. So what did we test? So we're asking ourselves, do R&B, rhythm and blues, and alternative songs differ in lengths? Okay, and we found that R&B songs average 242 seconds, alternative songs averaged 238.3 seconds. So if we were to subtract that, there's a difference of approximately 4.4 seconds. So our verdict after running this test is that while R&B songs are slightly longer in length, this 4.4 second difference is not statistically significant. The p-value, which was 0.544, is very high. So there's a 54% chance we'd see a difference this large just by random chance. But the practical interpretation would be that song length is basically the same across two genres. So that 4-second difference is not as meaningful in practice. Objective 2, construct and interpret confidence intervals regarding the difference of two independent means. So constructing a confidence interval for the difference of two means is an extension of the results presented in 9.2. To construct a confidence interval for the difference of two independent means, the following requirements must be satisfied. And these are the same 4 requirements that we've used in previous sections. It's the same requirements as the hypothesis test, so nothing has changed. Now to find confidence interval estimates for mu1 and mu2, we're going to use the test 0 to sample t int. Okay. When we were doing 1, we just used t interval. But now that we have 2 samples, we want to find the confidence interval. Make sure we use not pooled. So when we go into this test, we'll select either stats or data. We'll enter in all the information for sample 1, then all the information for sample 2, and then our confidence levels. Select no for pooled, and then calculate. So the aluminum bottle, the aluminum bottle first introduced in 1991 by CCL Container for mainly personal and household items, such as lotions, has become popular with beverage manufacturers. Besides being lightweight and requiring less packaging, the aluminum bottle is reported to cool faster and stay cold longer than typical glass bottles. Small Brewery tests this claim and obtains the following information regarding the time and minutes required to chill a bottle of beer from room temperature to serving temperature. Construct and interpret a 90% confidence interval for the mean difference in cooling time for clear glass versus aluminum. Okay, and so we have our stats here: clear glass, aluminum. We have our sample size for each. We have our mean time to chill for each, and we have our sample standard deviation. Okay, So we would go straight into our calculator for the 2-sample T interval, and we would enter in our data for sample 1, the clear glass, and then sample 2, the aluminum. Once we enter that in, press no for pooled, and then calculate, we would get the following confidence interval. Okay, so we have 2 positive values here. Okay, so we can say that there is significant difference between the mean cooling time for clear glass versus aluminum. The mean cooling time for clear glass is greater than the mean cooling time for aluminum. Okay, so what do the numbers mean? Well, our glass bottle chills at 133.8 in 133.8 minutes. Aluminum bottles take 92.4 minutes. So if we were to subtract these, that's a difference of 41.4 minutes. So an aluminum is faster. So what the confidence interval tells us is that we are 90% confident that the true difference in cooling times between clear glass and aluminum is between the confidence interval that we found, which would be the 38.1 and the 44.6 minutes. Okay. The key thing to note here is that the entire interval is positive. So that means that the glass bottles take longer to chill than aluminum bottles. Since the interval doesn't contain 0, this difference is statistically significant. Okay? So our practical meaning or interpretation would be that aluminum bottles chill about 40 minutes faster than glass bottles. So we would say this is both statistically and practically significant because there's a real advantage to having aluminum bottles than clear glass. And I would say, in my own personal experience, keeping my water, juice, whatever it might be, in an aluminum container does keep it more chilled versus a clear glass, hands down. All right. In a survey of 80 recent graduates with a bachelor's degree in engineering, the mean starting annual salary was $60,300 with a standard deviation of $10,822. That's a huge deviation. The same study surveyed 110 graduates with bachelor's degree in psychology and found the mean salary was $34,200 with a standard deviation of $10,698. Construct and interpret a 95% confidence interval for the mean difference in starting salaries. Okay. So we have our data for our first sample, which is engineering. Our sample size is 80. Okay. Our mean is 60,300, and our standard deviation is 10,822. Then we have our data for our second sample, which is psychology. Our sample size is 110. Our mean is 34,200, and our standard deviation is 10,698. So we would go into our calculator now to the 2-sample T interval, and we would then calculate our confidence interval. And we would get 22,976 and 29,224. Okay. So to interpret this, we would say that there is significant difference between the annual salary of an engineering graduate and a psychology graduate. The mean salary of an engineering graduate is higher than the mean salary of a psychology graduate. Okay, so let's understand this result a little more. So what do the numbers mean? So the engineering, let's go back. The engineering, here we go. Average was 60,300. The psychology was 34,200. So that makes a difference of approximately 26,100. So engineering is more than psychology. What does the confidence interval tell us? Well, we are 95% confident that the true difference in starting salaries is between $22,976 and $29,224. Okay. Remember, I'm saying the true difference in starting salaries. So the difference between engineering and psychology resides within this interval. Okay. So the entire interval here is positive again. So meaning that the engineering graduates earn significantly more. Since the interval does not contain zero, the difference is statistically significant. So practically speaking, engineering graduates earn more per year than psychology graduates. So this is both a statistical significance and a practical significance, especially for students who are choosing majors and planning careers based off of engineering and psychology. Okay. All right. That concludes section 11.3.